Hi, my name is William Sell, and this is my presentation for my final project for CS185 using Storm with an itch data feed. My goals for this project were to use Storm to parse a real-time data feed, the NASDAQ itch data feed, collect statistics in real time on this feed, and then to store into a database for later analysis. The NASDAQ itch data feed is a real-time market data feed, which includes all the trade messages for all the stocks traded on NASDAQ, which is roughly 3,000 stocks. Above you can see an output of my parser that shows what those trade messages kind of look like. This data is interesting because you can use it to construct in real time or reconstruct the limit order book. And if this isn't something you're familiar with, I encourage you to look it up. I'm not going to go into too much detail on what exactly the limit order book is and all of those details. And also in this data, there's quite a bit of useful market microstructure information on order submissions, cancels, executions, all types of things that could be useful to gather statistics on to possibly generate trading signals. Here's an interesting visualization from the people over at Nanex using the data we're discussing here. You can see the order book has been reconstructed and as it moves through time. Since the actual NASDAQ itch data feed is difficult to connect to and prohibitively expensive, for our purposes, we're going to replicate that feed using 1 day of data of this feed stored in a binary file in the NASDAQ itch 4.1 data format. There's a lot of it. It's about 3 gigs to download and about 7 gigabytes uncompressed. We're talking several 100 million messages in this one file. And it's not uncommon to see, 60,000 messages per second. And if you would like to download the example data that I used for my project and that NASDAQ provides for people to test, there's a link right there. So in order to replicate this data feed, I had to use this binary file, parse it, and then produce the trading messages. To do that, I had to build an entirely different tool, an itch data parser, just kind of my own library. Within that, I used YAML, which is a data serialization tool within a Java library called SnakeYAML. Basically, what you can do is express all of this logic about how the messages are constructed and put that into a YAML file, which there's an example of on the picture there, and then you can convert that into a data structure to help you parse the messages. So the library that I wrote to help parse these binary files is called itch parser. It will read in the binary file, parse it, and will output the trade messages. It'll follow the NASDAQ itch 4.1 message specification. If you look at the bottom of the slide, there's a link there kind of showing how the messages, or how the binary file is organized, and how to decode the messages from the byte arrays. Basically, you start at the beginning of the message. The first 2 bytes will tell you the message length. You can then use that to read all of the bytes for the message. The next byte following those first 2 bytes gives you the message type. Using that message type, you can now use those data structures that we previously mentioned, the YAML produced data structures, to generate the message from the byte array that you have. And as I mentioned before, you repeat this several 100 million times for each message in the file. Now that we've sort of replicated this real-time data stream, we can use the tool that we're we're interested in for this project. Storm. Um, as it says here, Storm is a distributed and fault-tolerant real-time computation stream processing continuous computation distributed RPC and more. It's a mouthful. But basically, just as I mentioned before, used for processing real-time data streams, large data streams. It was developed at Twitter. It's open source. I believe the guy who developed it is no longer with Twitter, off doing his own thing now. Used for real-time computation, and you can also run it locally or in a cluster. I believe that it's meant to be run in a cluster. Running it locally is kind of just a perhaps convenience, just to test your code. Okay. Some of the terminology of Storm, let's start with streams and spouts. Stream is considered an unbounded sequence of tuples, which would be our itch data feed stream that we generated with itch parser. And these tuples can be pretty much any data type. Itch, double arrays, byte arrays, string arrays, in our case, etc. So from this stream, they go into a spout, or rather a spout is a source of streams within Storm. So the spout will read these tuples from some external data source, in our case it'll be the itch data feed, and then we'll emit them into our topology. I'm going to get into what exactly that means in a couple slides here. And spouts can read from multiple data streams at once. Bolts and topologies. Bolts will receive emissions and perform functions. They can receive emissions. Recall that spouts emit values. Well, those values can go into bolts. Bolts themselves can also perform functions and then emit more values, which can go into other bolts. The kind of functions they can perform can be, aggregation. In our case, we're using them primarily to record statistics into a database, perform joins, etc. Finally, a topology can be considered the logic for our Storm application. At the highest level, it's kind of a definition of how exactly our spouts and bolts will fit together. The topology will also contain configuration data, on how many spouts you want running at a time, what level of parallelism you want. There's quite a bit of granularity. And this topology will process our incoming stream and run forever, or until you kill it. Something important to note here is that since it is running indefinitely, you need to watch for memory leaks. That's something I'll discuss in a little bit as well. So here's an example of the topology that I used. The stream, again, is our itch parser. The spout is our itch spout. The bolt is itch stats. And then that flows into itchdb, which I'll get into in a little bit here, which then stores the values into an SQLite database. Really, the only two parts of the topology that are actually operating within Storm are itch spout and itch stats. Okay, so now after our data has been generated at the stream, flowed into Storm through a spout, and then into a bolt, that bolt is going to want to communicate with well, in our case, communicate with the database. I chose SQLite. It's a really simple, self-contained SQL database. The source code is in public domain, and what's really cool is that it's zero configuration. There's nothing to install. You can just download some libraries, and basically that's it. Within Java, I'm using an SQLite JDBC driver. It's just a single jar library that allows us to communicate with and transact with the database. Really easy to include in your project if you're using Maven. Simply add it to the dependencies. There's more on that, I think, on their website if you want to check it out at the bottom of the slide there. So I wrote another library to communicate between our Bolt and Storm and the SQLite database. HDB will just simply connect the Bolt to the database. It'll take the output and then we'll write it to SQLite in predefined time frame batches. What that means is we're looking at specific message types, in our case, added orders. Only a couple different kinds of added orders. We're breaking it down by the order type and by the stock. You can see in the image there how our database is set up with the tables, and then also whether it's a buy or a sell order. These messages are all time-stamped at the nanosecond. So in my case, we're only looking at those two data types, or those two message types rather, and then we're looking at all messages within a 1 minute time frame. For each minute, we're looking at how many shares per category were added and then recording that. So each batch is 1 minute's worth of data. And HDB is responsible for kind of aggregating and doing batch writes to the database with that data. Again, we're only looking at two types of messages here, message type A and F. We are creating tables for each ticker, each order type, and also for a buy or a sell order. So 4 tables per symbol. I just did that for sort of a proof of concept. It's pretty simple to add additional message types to filter them in canceled or deleted orders. And also you can look at other statistics rather than just looking at the number of shares added. You can look at data points that are included in those messages, such as the MPID, the market participants ID number. Perhaps you think that that's an interesting thing to keep track of. And again, the time frame that we're using here is arbitrary of 1 minute. You can pretty easily change that to a 1 second time frame, 30-second time frame, whatever. The thing to keep in mind there is with a smaller time frame, there's going to be more writes to the database and more optimization needed in the code, because right now it's already fairly slow as it is. So the more writes you're going to do is going to slow that down even more. So moving on to the results. It takes more than 1 minute to process 1 minute's worth of this HDataFeed data. That kind of means that it's not ready for the prime time. There's a lot more optimization needed. On the bright side, the code does work. It generates the database with the tables and the statistics as expected. So that's good. Just a lot more optimization again. And one of my original goals was to capture the incoming feed and store the entire message stream in a database as it was coming in. This proved to just be too slow, even when I tried to batch up the messages. So I think I need to examine different solutions for capturing that feed. And to give you an idea of kind of how long this all takes, it took me about 12 hours to process 100 million messages, which those 100 million messages were only about 4 hours worth of data. So some takeaways that I got out of this project is that I definitely learned much more than I planned to. I spent a lot of time working on the parser, learning about YAML. Storm, of course, was something I was very interested in learning more about. I didn't have a great SQL database background, looking at big little endian numbers and memory leaks. I guess considering that the topology runs so many iterations, like I say here, little problems can become huge fast. So there are a lot of little steps, little things that you need to pay attention to within Storm to have the proper configuration, or again, you're going to see memory leaks and things are going to fail rather quickly. On the bright side with Storm, it's pretty easy to write a simple topology. Take a look at like a word count example that's out there and just get it to work. And even to boot up a Storm cluster on AWS, I think is pretty automated and pretty simple now. Um, Something else, Storm is probably better suited for a cluster than a local environment, which might be pretty obvious. I think the local environment is really only supposed to be used for testing. I don't know that for my specific implementation needs, I really have much of a use for Storm, but it's something I'm going to continue looking at, and that I have much more work to do to accomplish some of my goals with this project. So what's next? Moving forward, the things I want to continue working on with this project is speed. The processing speed was very, very disappointing for me. Whether I'll stick with Storm or not, I'm not sure. The message processing, parsing speed can be sped up. I know that there's some efficiencies to be gained on just some of the ways that I'm parsing those messages. I want to look at some alternatives to the SQLite database. Writes are very slow, but I need real-time access to these generated stats, meaning I don't want to emit things in a key value pair and then have to run some MapReduce job to aggregate the stats. I don't want to wait for that. Again, trying to back up the incoming stream was a goal of mine that I wasn't quite able to accomplish, but I'm looking at other strategies, other ways to do that. I have been working on a Java limit order book, which would be very interesting to incorporate into this somehow, and storing additional stats. Like I said, just storing the A and F add order messages was just a start. There's much more you can do here. And also, I'd like to work on a library then to analyze the generated stats in real time to, again, possibly make trading decisions on that information. And finally, I think I may be done with Storm after this project. It's an awesome product if you have the correct use for it, but in my case, I just don't know that I do. If you're interested in more of the details of my implementation, please take a look at my code. There's a lot more details in my write-up as well, or feel free to send me an email. Thank you.